Today, I'm pleased to introduce today's session, Designing Retrieval Augmentation for Generative Pipelines with Haystack, and our guest speaker, Tuana Çelik. And Tuana is a developer advocate at Deepset, where she focuses on the open source NLP framework to build LLM applications, Haystack. With a degree in computer science from the University of Bristol, she started her career as a software engineer, but then returned to the world of machine learning as a developer advocate and now dedicates her time to helping the open source NLP community. Tuana is also joined by my colleague, Yujin Tang, whose name I say 1,000 times a week. He is a developer advocate here at Sills. Welcome, Tuana and Yujin.
Okay. So today we are going to be talking about building retrieval augmented pipelines at scale. My name is Yujin. I'm joined by Tuana from Deepset, and I will actually let you introduce yourself first.
All right. Hello, everybody. Thank you for the introduction. Well, Emily said it all. I'm one of the developer advocates at Deepset, and I focus on our OpenNLP framework to build large language model applications called Haystack. So today I'm mostly going to be talking about Haystack, and this is all of my social media information. So if you do want to follow me, go ahead. And I think we can give it a start.
Cool. The QR code there, by the way, links to Tuana's LinkedIn. If you have your phone, you can scan it and go follow her or connect. I'll give 10-15 seconds for you guys to scan this, and then I'll go move on to my slide. Okay, so this is me. My name is Yujin Tang. I'm the developer advocate at Zillis. Hopefully we'll be joined by more developer advocates soon. That QR code links to my LinkedIn, so you can scan that and you can follow me or connect and send me messages. These are some of my links if you want to find me. My background is in machine learning, and I've been building a lot of these retrieval augmented generation pipelines recently. So today's outline is going to look kind of like this. We're going to start with addressing why you want to build a retrieval augmented generated pipeline. Then we're going to talk about how you can use a vector database for your RAG app. And then we're going to look at how you can build a RAG app pipeline in Haystack. And then we'll cover some frequently asked questions. These are just some questions that come up from time to time from our presentations. And then, at the end, you'll have your chance to ask questions as well. So, Tuana, want to take this part away?
All right, so we're going to do a bit of a back and forth, but I'll start with a quick recap as to why we talk about retrieval augmented generation. And to sort of depict the issue we try to solve with retrieval augmentation, I have an example, and I'm sure a lot of you have already seen this UI before. So this is actually a question I asked ChatGPT. And I asked, what time is the talk about retrieval augmentation? And as you can see here, I got a reasoned reply. Here I was using GPT-3. And the reply is that it simply doesn't know. If you're lucky and you're using a model that can do this, you will get a reply that says, I don't know. But in a worst case scenario, you might also get a reply that simply is a hallucination. We try to solve this particular problem with retrieval augmented generation. And to give you a bit of an insight as to why I asked that question, here's actually a screenshot of a meetup myself and Eugene are doing this evening. And you can see that at 6:25, there's a talk about retrieval augmentation by myself. And what we're going to try to solve is the following. Well, large language models do not know the answer to everything. And the idea behind retrieval augmentation is that we can help them by giving them the relevant context. And once that context is retrieved, the reason why we call it retrieval augmentation, at least this is how I imagine the name came up with, is that we augment the prompt or the instruction. We send these large language models with the relevant context. So for my previous question, the relevant context might be this particular event's data. What is this event about? What time are each of the talks, etc. So a retrieval augmented pipeline, at the end of the day, what it looks like is, it looks like us sending a prompt that looks like the following. We have an instruction or a prompt. And we've said, given the context, please answer the question. If the answer is not contained within the context below, say, I don't know. Now, this is just an example of a retrieval augmented prompt. And what I've done here, I've just gone ahead and copy pasted the event schedule for this evening. And then I have asked, what time is the talk about retrieval augmentation? And when I do this, then I get a reasonable answer. And this is actually a correct answer. The talk about retrieval augmentation is scheduled for 6:25 to 6:55 p.m. So what we're going to be talking about with UGN today is how you can actually build a pipeline that will do this for you, that will achieve this end result for your interactions with large language models for you. And the way we're going to be filling in that context is going to be the retrieval step. I'm going to come back to talk about how you build these pipelines with Haystack, but before that, I'll hand over to UGN to start talking about how vector databases play into this pipeline as well. So hand it over to you.
Okay. So we're going to talk a little bit about how RAG works, and then I'm going to dive into the vector database details later on. But the basic idea is that you have some sort of knowledge base that is not yet in ChatGPT or Llama or Vicuna or any of those big large language models. And you would take your knowledge base and you would put it into an embeddings model. An embeddings model is a deep learning model that is trained on the type of data that is the same type of data as the data that you were trying to work with. Then that deep learning model, the embeddings model, will produce a set of vectors as the output of the second to last layer. So in this little image here, you see that there's like this one node at the end. What actually happens when the embeddings are generated is that we cut off the node at the end and we just take the output from the second to last layer. And that's what a vector is. And those vectors get stored into some sort of vector database like Milvus or Zillis. And this is just the first step to RAG. This is just the step where you're putting your data into the application so that you can actually have a custom retrieval augmented generation app. I've been building a lot of these for the past few months, and typically what we see the stack looking like for retrieval augmented generation is something that we call CVP. And CVP stands for ChatGPT like LLM or ChatGPT or any other LLM. And this is typically the computational power behind these retrieval augmented generation apps. This is the processor. And if you were to think about this in terms of a computer, then you have a vector database such as Milvus. And this can be interpreted as the storage block. This would be your memory, your ROM. And then there's prompt as code, which essentially augments out the prompts to give a correct prompt to the LLM in order to get the response that you need. And an example of something that you can use with this is Haystack, which is mainly used for the orchestration of these pipelines. This is an example architecture of a application that we built that uses the CVP stack. So the application that we built is called OSS Chat. It is an open source software chatbot. Basically, it's at osschat.io. You can go check it out and you can ask it questions about open source software. The way it works is, as we showed earlier, you take your knowledge base. Step one is you take your knowledge base and then you embed it, you chunk it up, you embed it, you put it into the vector database. Then when the user comes and asks a question, the first thing we do is we actually hit the vector database and we say, is the answer in here? And if it is, then we can return that. And if it isn't, then we may have to go ask the LLM for an answer if it has one. There are some caveats here, right? You want to make sure that the questions that you're asking the LLM make sense and that you're not getting some sort of hallucinatory response back. And something that came out of OSS Chat is this thing called GPT Cache, which we made because we found that as we were creating OSS Chat and we were getting the answers to, or getting questions for these documents and generating questions that these documents can answer, a lot of the questions and a lot of the queries that we're giving the LLM came out to be the same. And so, or semantically similar enough that the answer would be the same. And so we decided to cache those responses, and that saved a lot of money, basically. So how do you use a vector database for retrieval augmented generation? This is basically what I've been building for the past few months. So step one, why would you use a vector database? Basically, what you want to use a vector database for is that you want to inject your own data into an LLM, or on top of an LLM, into an LLM application. And you want to you want to get relevant responses to what you're querying about and what you're asking about. And the LLM is not necessarily trained on the kind of data that you are using, or your data. In fact, most of the time, and I would say, it would be weird if it were trained on your data, especially if you have private data. And finally, the last reason why you would use a vector database for this, or maybe not the last reason, but a third reason why you would use a vector database for retrieval augmented generation is because the economics work out well. The other option that you really have if you want to kind of inject your data into some sort of LLM is you want to do some fine-tuning, and that is typically much more expensive than using a vector database and injecting your data that way. Okay, so what is a vector database? Essentially, a vector database is the database that you would use to store some vector embeddings and do semantic similarity. So how does this work? You start with your unstructured data. You typically have some sort of data that, most of your data is unstructured. It could be images, it could be videos, it could be some text documents, PDFs, some audio, it could be, something else like that. And you feed it into the right embeddings model, right? So it's actually very important that you make sure that you feed the right type of data into the right type of model. You don't want to feed image data into like sentence transformers, and you don't want to feed sentences into like ResNet 50. So once you have these vector embeddings, then you store them in a vector database such as Milvus or Zillis. And then from there, that's all you need to do to put your data into the vector database. That's all you need to do to put your data into the application. From there, what you are going to do is you're going to do the query step, right? So the querying is you take the same kind of data that you're looking for. So for example, if you're storing a bunch of image data that was vectorized using ResNet 50, you use your query, and you want to use the same model to get the vector embeddings from the input data that you that you're looking to query for. Now, there are cases where you might want to use a different model, and it took me a while to kind of figure out like why would I ever use like a different model for querying. And it turns out there's this thing called graceful degradation where you want to check against knowns against unknowns, and that's when you would use a different model for your query data to create your vector embeddings and check against the vector database. So I'm going to just cover a very quick example of semantic similarity. This is going to be a very, very simple example. There is no case in real life where you would ever use like a two-dimensional vector, and there are very few cases that we see, at least in terms of retrieval augmented generation, where you would use Euclidean distance. But this is a pretty famous paper, and it is about semantic similarity, and it illustrates the idea of semantic similarity with vectors very well. What I want you to get out of the next few slides is basically vectors allow you to do math on things that aren't numbers. And in this example, it's going to be math on words. So the example I'm going to show here is this one, is queen minus woman plus man equals king. So let's take a look at these. Let's take a look at these vectors, right? So queen is 0.3, 0.9, king is 0.5, 0.7, woman is 0.3, 0.4, man is 0.5, 0.2. You can see that queen and woman have some semantic similarity because they have the same X value. And you can see that queen and king have a similar relationship to woman and man because the Y value differs by the same amount. And you can see also the king and man have the same semantic similarity on the x-axis as well because they have the 0.5. Okay, so what happens here? So we'll take the word queen and we'll subtract the word woman. So we'll have 0.3, 0.9, 0.3, 0.4, and that gives us 0, 0.5. While this doesn't necessarily represent anything on our graph, we can kind of guess that this probably represents something like the concept of royalty, because what is the difference between a queen and a regular person? That's the royal status, right? And then from there, what we want to do is we want to add the word man, and so 0, 0.5. plus 0.5 comma 0.2 gives you 0.5 comma 0.7, which maps directly to king. So this example, very, very simple toy example, two-dimensional vectors, queen minus woman plus man equals king. So what does a vector database kind of look like? A vector database is basically, it's a purpose-built database for doing vector search. And the things that are very specific for vector search is, number one, you're going to be doing a lot of computations. Vector similarity requires you to do some computations in order to compare the vectors, right? And you need a purpose-built vector database for this because a regular SQL database doesn't do a lot of computations. Like, it is very rare that you're going to go into, I mean, I don't think it happens ever, actually. You go into a SQL database and you're like, give me 768 calculations right now. It's not going to happen, right? Typically, you're going to be doing some sort of maybe a bit mask, maybe some sort of like, joins, maybe some sort of comparisons, but that's about it. So that's why you need something like a vector database. In vector search and in search in general, there are three kind of separations of concerns. One is indexing, which is, how do you create the way that you search your database? One is data, which is data ingestion. How do you get the data into your database? And the last one is querying, which is, how do I actually ask the database for my results? And so Milvus has a separation of concerns with the query, the data, and the indexing nodes. And this is pretty unique to us as far as we know. And indexing, the index nodes takes care of the index. There are many different types of index that Milvus offers. There are many, we have a bunch of resources on that, and we can drop some links on that below. But some of the indexes that Milvus offers include hierarchical navigable small worlds, or HNSW, face, or inverted file index, also known as IVF. Data node, the data node is used to ingest the data. It reads the message store, the write-ahead log, and then it takes data and it compacts it, calls the indexing node when it's time to index, and puts it into sort of permanent object storage. And then the query node is used at query time. And so when you need to query your data, you use the query node. And typically the query node needs to be able to access both the permanent storage and the write-ahead log. So it knows what's going on right now and what's already been stored. And the reason for this is because Milvus has this really, really interesting architecture with the way that the data is stored. So the data is stored in 512 megabyte chunks, and every time one of these 512 megabytes comes along, we cut off these like segments, 512 megabytes at a time, and we create the index over that segment, over a 512 megabyte segment. And then that index doesn't change, and that segment doesn't get changed unless you force a reindex. And this is very, very good for scaling, because let's just imagine for a second, like, would you rather query 100 gigabytes in parallel or run 200 parallel queries on 512 megabytes? What's going to give you a faster response? It's pretty obvious that running the parallel query will give you a faster response. The other nice thing about these nodes being separated is that you can scale them up and down as you need. You don't need to scale up your nodes just because, hey, we're querying a lot, but we never ingest any data. So it's nice to be able to say, it's also economical to be able to say, like, we're just going to scale the data node when we're ingesting this data, and then we're just going to scale up the query node when we're doing a lot of queries. So that's what a vector database looks like. I'm using Milvus as the architecture here. So yes, they're purpose-built to be able to query large vectors and do a lot of calculations. So now we're going to talk about building a RAG pipeline with Haystack, and I'm going to hand it back over to you, Tuana.
All right. Okay, so before I start going through the pipeline itself, I do have to talk about Haystack. So Haystack is a fully open source framework built in Python, designed to build large language model applications meant for production. But not only that, Haystack also covers core NLP tasks, such as actually some of that Eugen also mentioned. In a lot of cases, if you do want to build an application that leverages large language models, it goes beyond just what you build with the large language model. There's a lot of data preparation to do, and you have to index into your database of choice. And then you have obviously the option of what kind of application you want to build. So Here on the right-hand side, I have one of the classic examples of two pipelines you might build with Haystack. One is called the indexing pipeline, which Eugene already mentioned. This is where you prepare your files, pre-process them, get them into the shape you need to get them into to be able to use these files in your LLM pipelines. And the second is the query pipeline. So I'm going to start with the document store. So in Haystack, you have the concept of document stores, and you have many options for different databases, Milvus being one of them. The second concept is the indexing pipeline, which we already sort of talked about, but here you have a bunch of options for different file converters, pre-processing, and this is important because depending on what kind of language model you want to use, you might want to chunk your data in different lengths, depending on what the context limit of that large language model is, and so on. And then the final step is probably the most interesting step, so we'll talk about this one particularly today, is an example of a retrieval augmented generative pipeline. The idea behind this is that a pipeline consists of a retriever, followed by what in Haystack we call a prompt node. And the retriever and prompt node act together to, at the end of the day, have an instruction that we can send to a large language model that it can work with and give us the correct answer to. And here you get a lot of options. You can decide to, for both the retriever and the prompt node, you can make your choice as a developer about what model you want to use to do your embedding search, or what model you want to use to do your answer generation. If you scan the QR code here, it should take you to the GitHub page for Haystack. So if you're interested, please go and have a look. And let's start talking about what components helps us build a RAG pipeline. In Haystack, the two most important components that you will modify and customize for your own use case for a RAG pipeline is the prompt templates and the prompt node. So I want to start talking about the prompt templates. The prompt templates is basically a blueprint of how you interact with a large language model. They are, at the end of the day, they generate prompts, but they can be modified, and they can be modified at query time. The prompt node, on the other hand, these are the nodes that interact with the large language model itself. They're basically the interface between your application and the large language model. They use the prompt templates to understand how to interact with those large language models, but they are essentially the node that will be sending out the query and then receiving the response from any model that you choose to use. Again, you have the choice of what models you do want to use. OpenAI models are one example, but you can also use open source ones such as Falcon and NPT. Llama is a new addition as well, and more. So at the end of the day, I just want to come back to this slide. What we want to get to is, instead of having our query being this to a large language model, we want to get to a scenario where we might be able to build something like this. The difficult part is, okay, but how do we fill this context? If we have millions and millions of data, how do we find the right context? And that is where the retrieval augmentation bit is going to come into play. So let's start by looking at prompt templating. So here, this is where we instruct the LLM on what to do with the provided information. So one example is you can build your own custom prompt templates. Here's a code snippet. There will be some code snippets following this. We're going to actually end up building a RAG pipeline in Haystack. And here I've built a prompt template called RAG question answering. And you can see the prompt is, given the context, please answer the question. If the answer is not contained within the context, below, say, I don't know. And then we have context and question. But the parts I want to highlight here are the things that you see in curly brackets. I've highlighted them with blue. Here we have the context with curly brackets join documents, and then question and curly brackets query. This means that the parameter called documents and query can get filled in at query time. And the neat part is that the documents parameter is by default set to receive anything from a retriever that might be preceding it. The next thing you can do is use the prompt node and define the prompt template that you just created as your default prompt template. So again, this is going to be our blueprint. It's going to be the prompt node's blueprint as to how it should interact with an LLM. So here you can see that I've made the choice to use GPT-3. And actually, I made the choice to use GPT-3 because it was the same model I was using in that ChatGPT screenshots I showed you before. Obviously, you're going to need your API key. And I set my default prompt template to RAG question answering, which was the prompt template I just created. The other option is, in terms of prompts, is to use some of the prompts that we've made publicly available on our new prompt hub. If you scan this QR code, it'll take you there. But this is quite a neat way of just making use of already available prompts without you having to design one out yourself. And you can set the default prompt template to one of the names of the prompts we have available in Prompt Hub. One example is, and I use this one pretty frequently, is called Deepset question answering. This prompt is already designed to do retrieval augmented question answering. All right, so we've got our prompt templates, we've got our prompt node. How do we actually build a RAG pipeline? So here is where we start talking about retrieval, and this is where we also start caring about what kind of database we use. So in this example, I'm using the Milvus document store. The Milvus document store is one of our integrated document stores. You can have a look at the Haystack integrations page to see all the rest as well. But it's super easy to get going. You just say document store is Milvus document store. This will set it up with all of the default parameters if you have Milvus running locally. And this means whatever data documents I have in the local Milvus database, I now have access to. I'm not going through the indexing pipeline, but you could have also done that to prepare your data to put into Milvus document store. Next is the retriever. Again, here you have a bunch of options. A retriever in Haystack, I'm using an embedding retriever here, is essentially the model you have decided to use to query your vector database. And I also saw a question come in about this, one of the first questions in Q&A. And yes, what this retriever node will do is once it retrieves a query, once it has a query from the user, it will create a vector representation of that query and then compare that to all of our documents in Milvus document store. That's why I also have to tell the embedding retriever what document store to work on. And then the final node is the prompt node. Here, I'm just going to use one of the publicly available ones from Deepset. And again, I'm using GPT-3. So I've got all of my components ready. And now I want to actually build out this pipeline. What I want to be able to do is, when a user asks a query, I want the first node, the first component in my pipeline, the query, to be that embedding retriever I just created. That embedding retriever then will query the documents I have in Milvus document store. And then I will embed the retrieved documents into the prompts for the prompt node to query the large language model. How does that look? I think there's a bit of a delay on the Zoom, but I'll start talking about it already. Next, you build a RAG pipeline. Could someone tell us in the chat whether you see the build a RAG pipeline slide? Because we see it on our side, but we don't see it on the Zoom.
We do.
Oh, okay.
Great. Okay, so next we're building a RAG pipeline. So here what we do is we, first of all, initialize a pipeline. And then, like I said, the first node I want to add is the retriever. And I set the inputs to query. In Haystack, by default, you have two input options that are kind of special. One is query and the other is file. The file is used for when you want to build an indexing pipeline, but now because I want to build a querying pipeline, the first input I'm deciding to use is query. And then simply I add a second node called prompt node, and I say to the prompt node that your input is the retriever. So any documents I get out of the retriever is now going to be embedded into the prompt node is using. And then simply I may run this pipeline with the same query to achieve the retrieval augmented prompt that we saw initially. The nice part of this is the following. As you can see, not only do I have query in this run function, I also have something called params. And these parameters can be provided at each query separately. And here I've decided to give the top K parameter to my retriever node. And this is important because depending on what model I've decided to use and how lengthy each of my documents in my vector database is, I risk the chance of hitting the context limit of the model I've decided to use. This is just an example where I've said, okay, my retriever, I want to only retrieve the top 5 most relevant documents from my database to query the large language model. If I was maybe using a model with less capability, I might decide to reduce that, or if I'm using a model with higher capability, I might decide to increase that. Each have their advantages and disadvantages. The advantages being if you have a higher top K, maybe you're giving more relevant context to the large language model to produce an answer with. But the disadvantage is you are then hitting you're hitting the limit of what the model can actually consume. I want to end this with an example application that you can see this actually working in. So if you scan that QR code, it will take you to a Hugging Face space. It's a public space. And the demo we've created is a retrieval augmentation demo with, I think this is using GPT-3. And we're just showcasing what happens, what the answers are when you do retrieval augmentation versus when you don't do retrieval augmentation. So you'll see 2 answers show up, answer with plain GPT and answer with retrieval augmented GPT. Not only that, but you can also try out retrieval augmentation with a static news data set. So what we mean is a data set that is a database that we connect to that has preloaded documents in there, and we are not changing it. But some cool things you can do is instead of using a database, you might simply want to do web search. So you can also see what retrieval augmented generation looks like with web search as well. And in this demo, we uploaded all of the news articles about SVB back in the day when that happened. And you can use either the data set we have at hand on this space or do web search. And that is it. This is how you build a retrieval augmented pipeline with Haystack. There's really not much to it, but there is a lot of creativity that you can add to it, especially when you're creating your prompt templates. That's where you can, essentially, you can even decide to not make it question answering, but summarization or anything else. It's a very creative process to come up with your own prompts. All right.
Cool. Thank you for that. That was a great explanation. Also, this is a very funny choice. Okay, I'm going to cover some FAQs that we get, and then we'll jump into question answers, or yeah, into the questions from the audience. So some of the FAQs that I get asked are when do you not want to use a vector database, or when do you not want retrieval augmented generation? From this, my response is typically, if you have data that is just key value stores and you don't need to compare similarity, you don't need a vector database, and that's not what you should be using in your retrieval augmented generation app. If you need to compare how similar or how semantically similar your input data or the data that you're storing is, then you would use a vector database for your retrieval augmented generation. Another question I get a lot is about vector embeddings around CSV files and PDFs. So one of the most important things for retrieval augmented generation is that you actually want to retrieve relevant data. And the most important part of whether or not you're going to get data that is the right relevance to you is your embeddings models. And so when you are doing work with CSV and PDFs, you need to really ensure that you're using the right embeddings models for them. I actually came across a use case recently where someone someone had input CSV models in, sorry, someone had input CSV data into their vector database, but they did not use a CSV like embeddings model to embed it. So they weren't getting good results because they used sentence transformers. Another thing that we get questions about is hybrid search, which is basically, we want to search structured and unstructured data. And can you do that with a vector database? The answer is yes. Milvus or Zilla stores metadata. Maybe you can't do this with everything. You probably can't do this with a vector search library, but you can do this with a vector database, and that can also help you enhance your retrieval augmented generation app. Okay, so let's get into Q&A. I have a question regarding vector similarity search. My understanding is, oh, by the way, this QR code is to a vector database benchmarking tool. I have a question regarding vector similarity search. My understanding is that the first step in retrieval augmentation involves embedding the query into the same vector space as the document vectors in the database. Essentially, this implies that the embeddings of the query should be semantically close to the embeddings of the potential answer. Is this assumption consistently correct? So there are, so yes. So yes and no. Okay, this is actually kind of complicated. So typically, the idea is that your questions, your queries are going to be semantically close to your answers, because you're going to be asking about something, and the vector database will search for something that is semantically similar to the question that you ask. Now, one way that we've seen this enhanced, actually, and this is actually kind of what I was talking about with the GPT cache in OSS chat, is you can enhance this by actually querying against the question space. And so what you can do is you can take your documents and you can go to ChatGPT or some other LLM, and you can say, hey, what are some questions that you could generate to answer from these documents? And then you have a question space, and you can also query against that. So the answer is yes, like your queries will probably be semantically close to your answers. And also no, because you can actually probably get better results by making a question space. So yeah, I hope that makes sense. Okay.
I think I can take this one.
Okay.
This question about how to overcome RAG DB vector limitations, if there are limitations, any changes or updates to large language models required for reindexing everything into the vector DB? Do you need the exact same LLM for querying? Can we change the large language model, or is it not allowed because it's defined within the vector DB? So actually, for the RAG pipeline, we're talking about two separate models most of the time. The large language model at the end, the large language model that we use to generate answers can be completely irrelevant to the model that you use to index and query your data in a vector database. So you've started to use ChatGPT or GPT-3, but you don't like the performance and you want to switch to Llama. That is totally fine. This is not something you have to worry in terms of your data in a vector database. Now, when it comes to indexing into your vector database, two things. Yes, you pick a model. It has a certain number of dimensions it's going to create for each vector. And then for your retrieval step, it's a good idea to use the same model, because then you want to create a vector representation of your query that has the same number of dimensions. And then that you can set up only for your embedding retriever step. There are some scenarios and some retrievers that do some fancy things where they can use a embedding model for your documents and use that model to embed your documents, but use a separate model, similar model, but separate model for your query. Again, they end up with the same number of dimensions though. So this is the only step that you should pay attention to. What model was used to index my documents into a vector DB versus to query? There's also a third question hidden in this one about what happens when you need to update your data. This does not mean you have to retrain or do anything to your large language model you use for querying. But this is why we have in Haystack a separate pipeline that I haven't gone through called an indexing pipeline. And whenever you have a new file, you can just run that file through your indexing pipeline, and it will embed that into your vector database the same way all of your other data is embedded.
I want to touch really quickly on this as well. Any changes or updates to the, I'm going to assume what you mean by the LLM here in this question is the embeddings model. If any changes or updates requires re-indexing everything in the vector database. So that is actually going to be up to you in the way that you implement it. It may, and it may not. You can actually take a look at what your performance looks like. This is what I mentioned earlier, is you may actually want to check that through this process called graceful degradation, where you're checking knowns versus unknowns. Okay, do vector databases have any limitations? For example, are there limits on how much data a database could index at a single time? Well, do vector databases have limitations? The answer is yes, they are software. All software has limitations. Milvus only indexes, Milvus pretty much only indexes 512 megabytes at a time because it takes chunks in 512 megabyte segments. The larger your data, that you need to index, the longer it's going to take. And so we typically say, hey, we're only going to index on like this size of data because it's more efficient, both in terms of like performance and in terms of like, financial value. So yeah, if there are other questions there that I may not have gotten at in terms of limitations, feel free to update this.
There's a question about, can you update a particular document into Milvus without re-indexing the whole database, meaning deleting the embeddings of a document? I can answer this from Haystack terms.
Sure, yeah. And I can talk about it from Milvus, so you can go first.
In Haystack terms, yes, you can do this with all of the document stores we have. Again, this refers to the indexing pipeline that I didn't really go into detail about. But the indexing pipeline, similar to the query pipeline you saw, is a pipeline you create and it's always there. And if there's new data that you want to add to your document store, then you simply run the indexing pipeline with that new file. And you don't have to delete anything. It just will write the new file to your already existing Milvus database. There are also options. This then depends on the database we use for the document store. To update the existing ones. So let's say we use this a lot, documentation sites, they're not new pages, the pages change. So in this case, you can flip a flag that means if the page was somewhat the duplicate, just overwrite it rather than deleting it and reintroducing it.
Yeah, Milvus has a similar kind of functionality. There's this concept called upserting, which is basically deleting and replacing a document. And you don't need to re-index your entire database for it. That would be ridiculous. Actually, in Milvus, one of the things that I think is really cool about Milvus is you almost never need to re-index because the indexes are only on very small like segments. Unless you're like deleting an entire set of like data, you really have almost no reason to re-index. Also, unstructured IO seems interesting to prepare the documents before being ingested into Haystack. Ben, Milvus, what's your opinions on that? Thanks. Do you want to talk about that, Tuana?
We've just started looking into this, so it's very new to me as well. So I'm not going to give you any solid answer, but yeah, we are looking into it.
I've got something for you. You want to pay attention to what's going on in my LinkedIn in the next couple weeks because I'm going to be releasing something about how you can use unstructured IO with Milvus. So enjoy and be on the lookout. Does Milvus support hybrid search, meaning combining vector search with something like BM25? That is a real help when working with domain-specific texts. So we do not natively support BM25 hybrid search. However, if you store your text chunks as metadata inside of Milvus, you can do keyword search on your metadata, and that is essentially the same thing. So the answer is yes, you just store your metadata in chunks. You just store the chunks of your text in the metadata and filter through that. And the filtering is really cool too. The filtering that we do is we use a bit mask, so it's once again, computationally inexpensive. Cool. Let's see what else in the chat. The QR code links to the source code. Okay. One challenge I found was that for enterprises, search costs can become prohibitive if prompts are sent to OpenAI. What alternatives, transformers? I mean, yes. You can use open source documents. This is also why we made GPT Cache. So I would suggest, checking out GPT Cache, which was what basically, like, we had the same problem, and we were like, hey, this is ridiculous. Like, we're paying a lot of money for this. And so that's why we made GPT Cache. It's a semantic cache that says, hey, like, if we've seen this query before, maybe just return the cache response. My customers say no to OpenAI for fear of security violations, confidentiality. So how can search RAG be done without LLMs such as OpenAPI?
I think we are getting more and more open source options out there. So that is definitely an option.
Yep.
All of this that I showed, the pipeline that I showed, is also stuff that we've tried with Falcon 40B and Llama, for example. So those are definitely options. And to the first point, that's where when you're talking about costs, that's where a lot of the pre-processing steps can come in handy. So for example, you might want to experiment with how you chunk your data, so that when you do retrieve the relevant documents, is it the whole 500 lines full of file that you're putting in there, or most relevant, 5 sentences you're putting in there, the top how many that you're putting in there.
Okay, so back to the Q&A. So you store the text kind of 2 times. I think this is the follow-up for the BM25. So the answer to this is no. You store the text once, and you store the vector embedding once. I'm not actually sure what you're asking here, but you don't need to store the text twice. You just need to store it once. If you want, you can also store the text in a SQL database. I'm not going to say you can't do that. And you can also, then, reference that and query that if you would like. That is up to you. I suggest that you just store it in the metadata and you use bitmask filtering because it's fast and it's easy. What happens when I need to update my embeddings because the source data was updated? If you're I think this is actually there's nuance to this question.
I think it comes back to the indexing pipeline side of things. When you have an update to your source data, this is where you look into reusing the same indexing pipeline you had for your original. And there are, again, I think Milvus, you also said that there's this capability, so it would work alongside Haystack. There are options to not say write documents, but to update documents, so that if it's the same file that has slight changes, you're not duplicating it, but you're simply updating it. And that's a simple function call. Yep.
My thought on this is it depends on how much your source data was updated and what you really need to do with that. So if you're changing your entire database, then you probably want to re-embed things. But if not, if it's small updates, I think you should just upstart, and that's fine. What are some options for image, CSV, PDF, video embeddings? Image, my suggestion is always ResNet 50. CSV, PDF, videos. This is where someone actually mentioned the thing about unstructured IO. They're doing something with PDFs, and that's actually what I'm working with them on. Videos are a little bit more tough. CSV is a little bit more tough. No one really works with CSV data that much. What I suggest to people who are working with CSV data and they want to do retrieval augmented generation is you should turn your CSV data into complete sentences, and that should always be possible. With whatever kind of data you're working with, and then you turn those complete sentences and you embed those sentences using a model like sentence transformers, and then you can query against that. Cool. So let's see. Yes, we'll open up we'll keep this open for a few more questions. Let's say, if you have another question in the next, try to type it in the next 30 seconds to a minute, and we'll try to get to it. Oh, so this comment, open source are still not good as as, oh, right, open source LLMs are not as capable as GPT.
Yeah, I agree. Right now, from my experience, this has been the case. But I've noticed that this is the case for, like you said, agents or very complex applications with large language models. In a lot of cases where you want to simply answer questions accurately, then the open source models are also quite good.
Another question, any general tips for best RAG performance when indexing and parsing source data? Yeah, you probably want to, well, there's this thing called context-aware chunking or smart chunking that is people are talking about a lot right now, which is how do you chunk your data in sizable chunks that make sense, that retain enough context that you can understand what the data is about, and also retain enough context that you can link them together. And this is not a solved problem. Like, nobody has solved this problem yet, and it is tough. But typically what I see for chunking is people do 512 character chunks with 25 character overlaps. Do you want to say anything about this, Tuana?
General tips, best RAG performance when indexing and parsing source data. This is an interesting one in terms of Haystack, because actually a lot of the times an indexing pipeline is not the type of pipeline you are continuously thinking about. A lot of the cases we see is that the indexing pipeline runs once, and you have your data, and then you have your RAG pipeline on top of it. When it comes to best practices for performance, my experience is, especially when you're talking about the pre-processing step, is really thinking out what length you want your chunks to be. And it all comes back to this more of the economic side of things. Is it going to be providing enough context for the large language model to understand what we're talking about? And is it going to be short enough that we're still within the limits of context size or the amount of money we want to spend if we're doing a closed source model?
Cool. I haven't tried Llama 2 yet either. Oh, by the way, Claude is actually, I don't know if you guys have used Claude, but Claude is interesting in terms of writing capabilities. I've talked to some people about this, and it seems that Claude does not edit you as much as GPT will. So you should check that out and see what you think about it. I think we are out of questions, and we are also about to run out of time. So I'm going to pass this back to Emily.
Thank you so much, Eugen. Thank you, Tuana, for joining us on this webinar. It was really great. And thank you to the audience for all of the really wonderful questions. We hope to see everyone on a future event. And for those of you in the San Francisco area, Tuana is going to be at the Unstructured Data Meetup San Francisco tonight. So you can come to the ZIL's website and check out more details about that, or reach out to us on our social channels. So thank you so much for everyone, and we will see you next time.